In this week's lab, we were given the task of building the simplest electric train using only a plastic tube, two spherical magnets, a AA battery, and an uncoated copper wire. We were told that the plastic tube was not needed to build the train. This led to the conclusion that the copper wire needed to be wound around the plastic tube and then taken off. We began painstakingly winding the wire around the tube, which took a total of about 5 minutes. Tyler and I became unsure on how the magnets and battery were meant to interact with the wire to create the train after that. Our first set started with us connecting the copper wire to each end of the battery and inserting the two magnets in the system as shown. This yielded no result as the magnets just sat there in the wire feeling rather sad. We then tried a few different combinations of three materials to no avail. We changed this setup of the train another time by putting a magnet on either end of the battery. We placed our battery and magnets in the coiled copper tunnel, and the battery and magnets began to move along the track by themselves. However, as we continued to investigate our train setup, we found that this method of connecting the magnet and the batteries did not always work. Oftentimes, the train would stop while going around the track, and we would have to shake or prompt the train to get it moving back along. Sometimes we would connect the magnets in a different way on the battery, and it would not continue through the tunnel at all. When the copper wire meets the ball bearing magnets on either side of the battery, our circuit is completed, as both the copper wire and the magnets are conductors. As the current was being generated around the wire, a nearly uniform magnetic field is being concentrated into the center of the coiled copper wire, the copper wire being referred to as a solenoid. The direction of this magnetic field can be demonstrated by the following right-hand rule, with the direction of the fingers being the direction of the current, and the direction of the thumb being the direction of the magnetic field. The current flows through from one end of the battery into the magnet. It continues through the wire and then enters the magnet on the other end of the battery and completes the circuit at the end of the battery. In other words, the only part of the solenoid that has current running through it is the region surrounding the battery. If only a magnet is placed inside the copper solenoid, it will feel no force and will not travel along the track. When the magnets are added to either end of the battery, this creates the force that moves the train. However, as stated before, the magnets must be in a certain array for a net force great enough to move the battery and magnet train. This meant that the force on both magnets had to be in the same direction. Although the magnets were spherical, they would still contain a north and south pole. We found it really hard to find which end of the magnet had the north and south pole, so it was really hard in our testing to find them. But the magnet in front of the battery was being repelled by the battery, and the magnet behind the battery was needed to be attracted to it. In other words, the front magnet gets pushed by the battery and the rear magnet is getting pulled. This creates a net force in one direction along the track. However, if both magnets' poles were flipped, the train would go in the opposite direction down the track. The world's simplest electric train gave many insights into the application of magnetic and electrical physical concepts, an interesting and fun experiment.
This is so epic!
This is truly